Okay, so let's talk about work, kinetic energy, and potential energy. You know what I'm going to do? It drives me nuts. I can't do it. I can't do it. Do it properly. Okay. Work, kinetic energy, potential energy. So there's me in my youth lifting weights. How's my form, Dan? Kind of choppy, yeah. Okay, so everyday sense, and you can highlight. There might be a couple things you can add into the notes that I give you. In the everyday sense, work involves pushing, pulling, lifting, basically applying a force, right? When we do work in here, all you're really doing is pushing a pencil around on the paper. I guess technically you are moving it. You are pencil pushers. It is work. You're not burning a lot of calories. So work is the measure or some measure of the amount of energy that is transferred when a certain force acts through a certain distance to do a job. Now the key words there are transferred. There has to be a transfer of energy. And for that to happen, there has to be a force and there has to be a distance. And we had that discussion yesterday about just holding something in place, right? There must be a distance traveled. Okay, so we're going to talk a little bit more about this work and transfer of energy idea here. So, it's been a while since I used these slides. Suppose you have a horizontal force applied to a dynamics cart for a certain distance. Work is done. How come? Because energy is transferred to the cart. The cart now has kinetic energy, right? So it's here at rest, right? And then you apply a force to it. So now later, I'll use the cartoon notation, the cart is now moving, so it has kinetic energy, right? You have transferred energy to that cart. Will that cart eventually slow down? Yes, it will. How come? Friction. Where does the energy go? Heat. I pointed you because I knew the answer. I knew you knew the answer. It's transferred as heat, exactly. Note, and this is not something we looked at yesterday, but you probably already knew it, but it wouldn't hurt to be reminded. When a force is applied at an angle, the cart moves horizontally. The only force which does useful work on the cart is FH, or we are now calling it FAX, right? Applied force X component. So in other words, when you've got something like this, the FAX is what's important. Right? That is the one that is doing the work. Okay, so potential energy. So say you are dressed all in brown and you're carrying a box, right? When you lift the box, you are doing work. When you're just standing there holding the box, no work. What if you're carrying the box down the hallway? No work. How come? You're not changing, there's no transfer of energy, right? I guess you could argue, well, it's now moving, you've increased its speed, that is true. You do a small amount of work, but you're not actually doing work as in you're moving at a constant velocity because you're not gaining any. You're only doing work when you get it up to speed, right? Okay, so as I was saying here, when objects are lifted, work is done, i.e. a certain force is exerted through a certain distance. Energy is used up or transferred to get the job done. But the kinetic energy of the bricks is zero. They are at rest. Where did the energy go? We say that it has been transformed into potential energy, which is stored inside the bricks. Now, is it physically transferred? Like, is it like a bank account or making a payment? Like, if I give Dan 20 bucks, is there some actual transfer happening, physical? No, I mean, it's kind of theoretical, right? You are changing its position. Can energy be seen? Like, can you put on special energy glasses and see it? It's really hard to sort of scientifically define. And Bia's example yesterday was perfect. It's the ability to do work. That's what it boils down to. Okay, so potential energy is energy that is stored in an object because of its condition or position. Most people think of position raised up in the air, but it could be its condition, right? You take a rubber band. I think I actually have one. That's what I'm supposed to be doing my physio on my ankle since last June. I'm lugging back and forth. I do have I'm lugging this back and forth for about 6 months. Okay, so here's some surgical tubing, and if you stretch it, careful, it has potential energy, right? To do work, right? I mean, it can. Well, maybe not. Do work, right? So it's condition as well, right? Whether it's stretched or compressed, I suppose. When we push, stretch out, or push in a spring, we do work on it. We transfer energy to it. We say this work goes toward increasing the potential energy of the spring, and we will be talking about springs and doing a little lab on them as well. In general, anytime work is done, energy is transferred to an object and either increases its kinetic or potential energy of some kind. There has to be this transfer. That's the key idea. Okay, now I showed you the formula yesterday, right? Here's sort of the formal derivation. I think I'm actually supposed to formally derive it, am I not? Is it on that list? I think it is, right? So I guess technically this is the formal derivation of work. So work is, what's this funny looking symbol? Anybody know? Come on. Told you before. It's the proportionality, right? Work is proportional to the force. The more force you apply, the more work you do. Proportional to. Right? Work is also proportional to the distance moved. The greater you apply the force, the greater the amount of work. Work is not related to time. Whether you do a job fast or slow makes no difference. It still takes the same amount of energy because it's the same job. It's the same transfer of energy. So with those in mind, work is proportional to F times D. Right? Work is proportional to F times D. Now, in the old days, I used to talk a lot more about this kind of stuff. With computers now, I don't need to as much. But so this translates to work equals KFD. When you go from a proportionality statement to an equal statement, you need to institute or bring in what is known as a constant of proportionality. Proportionality. Hard word. Constant of proportionality. This happens all the time. Right? Okay. Way back in the good old days of grade 11, you probably did a lab. I think many of you did it with me because I think I was still around when we first started the right? And we know that circumference is pi times d, right? You know that formula from probably about grade 7, right? Well, and it's because that the circumference of a circle is proportional to the diameter. The bigger the circle, well, the greater the distance around, right? The Egyptians knew this. They knew that the circumference was proportional to the diameter. So they wanted to know what was the magic number, right? And so when you take the circumference and divide by the diameter, it doesn't matter what circle you'd use, the circumference divided by the diameter always comes up with 3.14, exactly. 3.1415926 and so on, right? Which we now know as pi, right? So pi is the perfect example of a constant of proportionality. Now, why is the k value 3.14 here? Well, that's just nature. The circumference of a circle is 3.14 times the diameter. It's just the way it is, right? There's no way around it. However, I showed you yesterday that work is equal to FD. So what happens to the K here? Well, because work is kind of a theoretical, like you can measure the circumference of a circle, but you can't go out and measure how much work is done. It's kind of an invention of humans, right? So we simply define 1 Newton, 1 force, 1 Newton, and 1 meter equal to 1 joule. We set the K equal to 1. Why did we set the K equal to 1? Because it's easy. Why would I want to make it some crazy number? Why would I make it 6.47? It doesn't make any sense. So we just set the value of K equal to 1. And in other words, the K doesn't even exist. Okay? So the unit for work, the basic unit is called the Newton meter, which we know as the joule. That is it Robert or James? Can't remember. Mr. Joule. Got a good beard. He was the original hipster. And 1 joule is the amount of work done when a force of 1 Newton acts through a distance of 1 meter. So we set the K value to 1. And we get work equals FD, which is what I showed you yesterday. It's actually right here. Sorry, man, I should have got that figured out. Okay? So that's literally the formula derivation. It's kind of an invented one. There's not a lot of math involved. We set the K value equal to 1, and that makes it disappear. Work equals F times D. And that's really all I got to show you. Okay? I should, though, however, from yesterday, I should go through. Did I put it here? I hope so. Oh, no, you guys over here. Oh, by the way, Monday we'll be back in my regular room. Because they're all done painting. I just have to do some kind of putting stuff away. That was taken off the wall. Can we go spend 5 minutes going through this one and then I'll be quiet? Did you get this one? It says calculating work done in various situations. It's a double-sided thing. Does anyone need this one? And if you haven't written the momentum test yet, well, you're running out of time. Okay, so all this does is to sort of give you various situations and sort of some rules, I guess, for how to calculate work done. And this does expand on some of the stuff that we've already talked about. So case number 1 is basic, as simple as you can be. I don't even need to read it. You apply a force, it goes through a distance. W equals FD. Why does it say no work done there? Consider, you need one of these two, Will? Yeah. Weren't you not here yesterday? Yeah. How did you forget? There was one of every pile. I know for a fact some of you are going to find them later. Because I have lots of the other ones. I would have just. Okay, I made like extra, Joel. Right here. Oh. You know you have to actually, flip. Thanks, Nick. See, now I don't have one. You know why I don't have one? Did I tell you about the organizational binder? Did I tell you guys that? Did I say that yesterday? Big binder, yeah. Here's my original. You can't have this one. Okay, maybe I better read it. Case number 1. A force acts on a mass and accelerates along a frictionless surface. Oh. Or if friction is present, the object might just move along at a constant velocity. In either case, energy is transferred to the mass, work is done by the force, and it can be calculated with W equals Fd. But consider motion at a constant velocity across a frictionless surface. Once the object is moving, no force is required to maintain that motion. That's the whole object in motion stays in motion thing. No work done. How come? No force applied. Case number 2, when an object is lifted vertically, work is done against the force of gravity. Note that the force needed is equal to the weight of the object, which is equal to m times g. So what is the work done in that case? If you're lifting something against gravity, the work is going to be the weight force times the distance, right? Or mg times d. Case number 3, an object is tied down and can't move. If it can't move, no work. When one goes over and pushes against the wall, it's not doing any work because it's not going anywhere. Okay? Case number 3, supporting forces. Pole exerts an upward force on the mass to support it. Maybe it's like a statue sitting on top of a pedestal or something like that. Since the distance moved to 0, no work done. There's a lot of these where no work is done. It's kind of like on a snow day. I've made that joke every semester since like 1999. What about a really skinny bald-headed man carrying a briefcase with his arms outstretched like that? Man carries a briefcase at a constant velocity. The only force he exerts is the supporting force. There is no motion in the direction of the force, and once again, no work done. That's one of my first self-portraits there. What about moving in a circle? Now, usually I do this unit after we talk about circular motion. So circular motion isn't something that you're that familiar with, but let's have another look here. After 5 revolutions or 10 revolutions, etc., the body has the same velocity and hence a constant amount of energy. Thus, we conclude that the centrifugal force does no work on the body. In general, there is no energy transfer or no work done when a force is exerted on a body perpendicular to the direction of its motion. So when you whipping a thing around your head like this, once again, no work done. Hey, these are easy, right? What's the answer? Zero. No work done. What about force exerted at an angle, pulling on a wagon or sled? You can pull in the direction of FF, but the object moves horizontally, i.e. in the direction of FX. Now here they talk about components. This sheet is like about as old as I am, I think. So let me just explain this diagram here. All this is just a different version of something you've seen before. So F perpendicular, this is Fx, and this is F here, I guess. So really, in modern terms, what we're talking about here, this value here is really, let me leave that in there maybe. This is really FAX, and this would be FAY. So that was the perpendicular force. Just a different notation. Okay? And so at the very bottom there, work is the component of force in the direction of the motion times the distance. In this case, work equals FD cos theta. Can we just go with that formula? FD cos theta, that's equivalent to what? It's FAX times D, right? Because F cos theta is FAX. That's all that is. This sheet needs to go away. I need to stop using this sheet. Well, that's just, I don't know. I need to add on. Okay, I'm tired of talking. You guys are tired of listening. I strongly suggest you do some work. Now, we haven't talked too much about power. I see some questions here that have power in them. You can ignore those for the time being. There was a second set. Can I remember that? You can do some of these questions as well, right here. Joel, you should put the phone away and listen. You're not really hiding it very well. You do have this period, as I said before, Monday, kinetic energy would work. Tuesday will be potential energy. Wednesday will be spring energy, and then we got to throw a lab in there. And we're aiming for that test. What did I say? Was it Tuesday?
Wednesday. You definitely said Wednesday.
Was it Wednesday?
Friday. Is next Friday?
Yeah, Thursday is the last day of
Day
school, right?
Day before.
Okay, so that's where we're aiming, and if we get it done, if we're ready to go early, then that's great. I need some momentum tests done.
Monday.
Okay, you have the period. Don't waste it.
Okay.